High impedance bus differential protection scheme. Here we are going to discuss the high impedance bus differential protection scheme. In a substation, each feeder, including lines and transformers, is separately protected by its own protection scheme. So if a fault occurs in any of the feeders, the associated relay of that feeder will trip the circuit breaker of that feeder only and isolate the faulty feeder from the system. But consider a situation when a fault occurs in the bus bar itself. If a fault occurs in the bus, which feeder or which circuit breaker will trip to isolate the fault, since it is not associated with any particular feeder? Therefore, for the bus, there should be a dedicated protection scheme to protect the bus if any fault occurs in the bus bar itself. A high impedance bus differential protection scheme performs this task. Suppose a fault occurs in the bus. Naturally, a number of incoming feeders are connected to the bus, and a number of outgoing feeders are also connected to the bus. Those connected feeders feed different substations and different parts of the grid. If we isolate only the incoming feeders for a bus fault, that will not be enough. Because if the outgoing feeders remain connected to the bus, there is a chance of backfeeding from the grid, since all substations are ultimately connected to a common grid. Therefore, our scheme should be such that when a fault occurs in the bus itself, all feeders, including transformers, incomers, outgoing and incoming feeders, should be tripped to isolate the bus section from the system. Otherwise, complete isolation of the bus cannot be achieved. Here we apply the bus differential protection. There are two kinds of bus differential protection normally used. One is low impedance bus differential protection, which is very popular nowadays, and the other conventional method uses a high impedance relay. In this video, we are going to discuss the high impedance differential protection scheme for buses. This is very similar to differential protection for transformers or differential protection of transmission lines. But here the protected zone is only the substation bus, not the transformer or transmission line. That is the difference. We connect one terminal of all the CTS together, irrespective of incoming or outgoing, and all CT secondaries of the same dedicated core for the bus protection are connected together to form two common points. Another important point is that in this scheme, the polarity of all CTS should be the same. Only then will the actual differential equation be properly applied. We connect the P1 primary terminals of all CTS toward the bus. This is general practice. Now, if we connect all S1 terminals together and all S2 terminals together, there will be no current flowing from S1 to S2, even if we short-circuit these two terminals. This is because the summation of currents of all incoming feeders will cancel out the summation of currents of all outgoing feeders. For a simple example, suppose there are two outgoing feeders and one incoming feeder connected to this common bus. The P1 terminals of the CT primary for the two outgoing feeders are connected toward the bus, and the P1 of the incoming feeder or transformer bay is also connected toward the bus. The currents through the two outgoing feeders are in the outward direction at a certain instant, while the current through the incoming feeder is in the inward direction. Let the outgoing feeder currents be I1 and I2, and the incoming feeder current be I3. If the secondaries maintain the same polarity, we can assume that at any instant, the secondary currents of the outgoing feeders enter through S1 and leave through S2, while the secondary current of the incoming feeder enters through S2 and leaves through S1. Thus, the polarity of the secondary currents of the two outgoing feeders is opposite to that of the incoming feeder. If we add these three currents, taking the outgoing feeder direction as positive and the incoming feeder direction as negative, the total current is I1 plus I2 minus I3, which will be 0 because the total current entering the incoming feeder is actually divided into two parts, I1 and I2. As per Kirchhoff's current law, if we consider the bus as a junction, the sum of all incoming currents equals the sum of all outgoing currents. The sum of the currents entering and leaving the node is 0. Therefore, the resultant current is 0 and no current will flow through this path. If we connect the relay here, nothing will pass through it and the relay will not operate. This is the basic concept of differential protection or bus differential protection. Now, we will proceed to the step-by-step actual explanation of the high impedance bus protection scheme. Suppose a fault occurs at that point of the feeder. The fault current of that fault will be contributed by this incoming feeder or transformer and by this outgoing feeder. All because here we have considered that this outgoing feeder is connected to another power station and that power station is a part of the power network connected to the grid. So the fault current shows the replica of the fault current at the secondary of the CT in this direction. And obviously the secondary current of the CT of the incoming feeder will be in that direction and the secondary current of the CT of this feeder will be in this way. So the current is coming out here to the fault path and two currents are entering it. Therefore, if we consider that point, then we will see the fault current is leaving out from that point and the contribution current to the fault current is entering into that point from these two feeders, the incoming feeder and the second outgoing feeder. So as a result, obviously, this fault current, which means the secondary replica of the fault current, is nothing but the summation of the secondary replica of this current and that current. So as per Kirchhoff's current law, the summation of these three currents will be 0. That means here all I1 plus I2 plus I3 equals 0. So no resultant current comes to this one, meaning the terminal of the relaying arrangement. So there will be no current flowing through the relay, so the relay will not act. But as the fault occurs here at that point, the protection relay dedicated for this feeder, or you can say activated with this feeder, will actuate the tripping of this particular circuit breaker and isolate this feeder from the system. But the differential relay will not operate in that case. Now suppose a fault occurs within the bus. At that moment, all the feeders, irrespective of incoming or outgoing, will feed the fault point. Because all the feeders, including the outgoing feeders, are also connected to the power network in some way. This outgoing feeder, the incoming feeder, and that outgoing feeder, in our example 3 in total, together will feed the faulty point on the bus. Now observe the direction of the current. The current through this outgoing feeder flows towards the bus. The direction of the current through the incoming feeder is also towards the bus, meaning towards the faulty point. The direction of the current of the other feeder will also be towards the bus, i.e., towards the faulty point. So obviously Kirchhoff's current law will no longer hold. Here, I1 plus I2 plus I3 does not equal 0. That means these three currents will not cancel out each other. Therefore, there will be a resultant current, a non-zero summation of the currents, and it will flow through this relay. I have already mentioned that this relay is a high impedance relay. That means the relay will have one coil inside it, and when the current flows through this coil, a voltage will be developed across the coil or inductor. As this differential current increases, the voltage drop across the relay coil will also increase. When it crosses its preset threshold value, the relay will actuate and send a signal to the trip relay of all the individual circuit breakers associated with that bus. This relay will send the signal to the trip relays of these circuit breakers simultaneously. As a result, all three circuit breakers will trip, and the faulty bus section will be isolated from the rest of the system. This is how a high impedance differential protection scheme operates to protect a substation bus. So, a high impedance relay is a current-operated relay, but it actuates the tripping depending upon the voltage that appears across it due to the spill current flowing through the relay. Now, let us come to the point. What is spill current? Spill current is nothing but the differential current. It flows through the differential relay when there is current imbalance occurring in the differential circuit. So again, when there is spill current flowing through the relay, there is a voltage drop across the relay. Obviously, there will be a voltage drop, and when this developed voltage crosses a preset threshold value, the relay activates its mechanism and trips the circuit breakers. Now, in many cases, we need to provide a resistor in series with the high impedance differential relay to stabilize it and prevent maloperation. Let us discuss. We all know that there may be a situation when any of the current transformers connected in parallel becomes saturated, meaning the CT core gets saturated. Then, even under normal operating conditions or during external faults, current imbalance occurs and spill current starts flowing through the relay. This spill current may cause the relay to operate even without any actual bus fault. So we need to first examine what will be the maximum possible spill current that can flow through the relay in the event of one CT core saturation in the system. Then we set the operating voltage of the relay, and this voltage should be above that value to prevent maloperation. This resistance is called the stabilizing resistor. Suppose the CT gets saturated completely. Then, the magnetizing reactance of the CT secondary winding will no longer be present, and this portion may behave as a short circuit. If we consider this loop, the reactance of the CT coil and the reactance of the relay coil both are very low and can be neglected. If we neglect those, then due to the secondary current, which is theoretically the reproduction of the primary fault current of the CT, as we assumed, a through fault at that CT, the CT becomes saturated. So theoretically, the secondary current will be the reproduction of the fault current through the CT primary. This fault current, when divided by the CT ratio, gives the CT secondary current. If we multiply this secondary current with the CT secondary resistance, including CT winding resistance plus lead resistance, we will get the actual voltage that will appear across the coil of the differential relay. Now, because the other CTS are not saturated, they supply balancing current. If we neglect the saturated CT for the time being, then the remaining CTS balance each other, and there will be no spill current and no voltage across the relay. So the only voltage that will appear across the relay is the voltage due to the saturated CT during the fault condition. As we just calculated, if this voltage appears and the relay starts actuating, then the relay may trip all the circuit breakers connected to the bus, thereby isolating the entire bus. But in the case of a through fault, we only need to trip the circuit breaker of the faulted feeder, not all the breakers. To prevent this, we set the operating voltage of the relay above the possible voltage developed during CT saturation, called the stabilizing voltage. Below this voltage, the relay will not operate. A safety factor, typically 1.5 to 2 times the stabilizing voltage, is applied to determine the pickup setting of the relay. During an internal bus fault, the spill current is very high. This produces a much higher voltage across the relay coil, which exceeds the threshold setting, ensuring that the relay operates correctly to trip all the circuit breakers and isolate the bus section. Now, let us come to the Metrosil. Metrosil is connected in parallel with the relay. It is a metal oxide varistor, MOV, which becomes conductive beyond a preset voltage. Metrosil safeguards the relay because during very high spill current, the voltage developed across the relay may rise far above the stabilizing voltage, which could permanently damage the relay. To prevent this, once the voltage exceeds the rated level of the Metrosil, it provides a parallel low impedance path. The excess spill current bypasses the relay through the Metrosil, thus protecting the relay from damage. Hope you got the idea. Thank you.
If you found this helpful, don't forget to subscribe, like, and tap the notification bell. Got questions or want us to cover a specific topic? Leave a comment. Thank you.